The National Association of Home Builders reported that 53% of young people, and what they're claiming here is way back in 1980, they're stating this as a fact. And they're saying way back when the population proportion was 0.53, back in 1980. They're not doing a sample back in 1980. They can't go back in time and do a sample. So what they're doing here is they're saying, you know what, just for reference, just assume that back in 1980, this 0.53 was in fact, and 53% of young people did in fact live at home with their parents. All right, so here we say, suppose in a recent survey, a sample of 231 young people, ages 18 and 24, found this many. So this is a frequency. This is not a mean. It's the number of individuals out of the 231. So we can actually calculate the sample proportion. They don't give it to you anywhere in here, but they do give you the information that you need in order to calculate it. You just take the 135 and divide by 231, punch that on your calculator. I don't think it's going to work out to a nice number, but it's approximately equal to 0.584. So you can see that it looks like in a recent survey, so we'll say that this recent survey is, say, 2019, it looks like the percentage living with their adult children living with their parents did go up. This number here is higher than what it was back in 1980, right? So it looks like about 5 percentage points higher, 5.4 percentage point higher. So we see it's higher. I wonder if that observed difference that we're seeing here is statistically significant. All right, so test using, all right, so here's our step 2, alpha equals 0.10. Whether the percentage of young people age 18 to 24 living with their parents has changed since 1980. Well, back in 1980, it was 53%. Corresponding proportion would be 0.53. So to suggest that it has, they're asking the question, determine whether it has changed. If you want to turn that statement into a claim, just state it in the affirmative, that instead of determining whether there's a change, say that there has been a change. All right, so the claim that we're going to test is that there's been a change in the percentage of young adults living with their parents since 1980. So if it's changed, then it's not the same. And the population proportion today is not the same as it was back in 1980 when the percentage was 53%. So here's how we would write a hypothesis using a population proportion for something has changed. And the reason we do the not equal to is because it doesn't say here that the proportion has increased. It doesn't say that it has decreased. It just says it's changed, and it didn't indicate direction. That's why the not equal to. Because of the not equal to, that claim has to be in the alternative hypothesis. Same variable, same number in the null, but in the null we have the equal to, and this number right here is the P0. So population, what's claimed to be true back in 1980, and we have the sample statistics from our survey in 2019. We do have to define the variable. There's only one variable used here, it's P. So we'll define P to be the population proportion of young adults living at home with parents. It's a population proportion, and so that's how I started out. And I just have to describe which population proportion it is. That's step one. Step two is up here, level of significance. Step three, this is a problem about proportions. All right, so go ahead and type everything in to where you need to type it in. And then I want you to report in the chat box the p-value and the test statistic. So I'll give you, hopefully you've had a chance to do this already, so you just have to go to the chat box and, okay, so enter test statistic and p-value. I'll give you a minute to do that. And p-value. If you don't want to report to the entire group, then just send me a message. I'm more interested in assessing the numbers that you get. Okay, those are all looking good. And so that means that you selected the correct test. One prop z-test, this is what we use for proportions. If you tried to use t-test here, you'd get down to the row where it asks for the standard deviation, and then you'd be stumped because there's no standard deviation in a problem like this. First thing it asks for is the p0, this number over here. And then it asks for x and n. And with those two, it can calculate the p-hat. And the next thing it's going to ask for, because we have so many p's running around in these problems, instead of just saying the population proportion and using p like we have over here, it uses an abbreviation prop. And we see not equal to p0 in our alternative. And you're correct. This is now a z-score or a z-test statistic. The calculator just calls it z, but this is 1.657, as many of you indicated, rounded to 3 decimal places, and the p-value rounded also. I'm going to give you 4 decimal places if you round it to 3 places. And if you round it to 2 places, so you probably don't want to round to 2 places. So 3 places or more. Four, we have p is 0.0975. We have alpha, which is 0.10. And 0.10 is larger than this. So p is less than the alpha value. So p is less than alpha, so we're going to reject. And then the conclusion is going to be similar to the previous one. Because we rejected the null hypothesis, we're showing evidence to support the claim. So there is sufficient evidence, there is enough evidence to support the claim. All right, there's kind of the boilerplate language, and now we just have to go write this claim. So we'll start with, instead of just writing P, we're going to write all this verbiage that describes P. That the proportion of young adults living at home with parents, okay? So all of that was just defining this variable, and then is not equal to 0.53 is what we can say. It's not equal to 53%, but it probably makes more sense just to use the language that they used up here. That the proportion of young adults living at home has changed since 1980. Yeah, Yeah, our evidence shows that, more young adults are living at home with their parents. That's what this test shows. We're not saying it's fact. We're not saying, hey, based on our study, this proves that more young adults live at home with their parents these days than back in 1980, because no one study proves anything. All right, and then I've given you a couple of problems here. And this one is it's similar to the other one where we use alpha equals 0.05 instead of alpha is 0.10. And so everything else is the same, but as soon as you get to step 4 and you compare P and alpha, the p-value is still going to be the same. We still have this two-sided test, but now alpha is 0.05. And this number is larger than 0.05. So P is greater than alpha, so our decision would be not to reject. So again, there's 2 reasons why you don't want to be very confident in your conclusion here. One is that it's based on one sample of millions. It could be an accurate sample that represents the population, or it could be one of those, most extreme 10% that do not. So we don't know which one we have. So that's the first thing. And the second thing, as you can see here, our decision sometimes is based on an arbitrary choice of our value of alpha. Okay, so the decision is going to change as well, because in this case we failed to reject. So we don't have enough evidence to support the claim. So once again, there is enough evidence? No, there is not enough evidence to support the claim. So we just want to insert the word not in the conclusion. But the conclusion will change a little bit. And in problem 7, we're going to change the claim again. But the difference in this problem is we're going to change from a two-sided test down to a one-sided test. And you can see it here. Test the claim that the percentage of young people living with their parents has increased. So the proportion is larger than 0.53 is what the claim would be. That's going to change the hypotheses. Not the null hypothesis, but the alternative it'll change. Alpha is not going to change. Same as the very first problem. And the test statistic is still going to be the same. You're still going to find 1.657 because here's the test statistic in this setting. And the 0.43 hasn't changed, 53. And that doesn't change this or this. And the sample size has not changed by changing the claim. And the sample proportion hasn't changed. So all of this stuff will be the same. So the test statistic will be the same. But the p-value, since we're going from a two-tailed test up here to a one-tailed test down here, the p-value would be exactly half of that. So 0.0975 divided by 2 is about 0.04, I'm just going to call it 9. Half of 0.0975. That's the relationship between the p-value in a one-tailed test and a two-tailed test. So that changes. And you can see now that because we're taking exactly half of that, this number here remains less than 0.10. So the decision's not going to change. Everything else is going to be the same. It doesn't make the evidence any stronger if we reject the null hypothesis with a p-value of 0.098 versus 0.049. The decision will be the same. We will write it up exactly the same way. The fact that the p-value is half of what it would be up here does not change anything about how we write the conclusion here. Okay, so same decision, reject the null hypothesis, and then same conclusion. And let's do one more problem like this. This one here is a two-tailed test. This is about a proportion. So we're working with the Z distribution. Remember, that's the normal distribution. Did a lot of work with this distribution. 0 is kind of right in the middle. And alpha is equal to 0.10. In a two-tailed test, we have two regions, two critical regions. We don't know if the population proportion is not 0.53, we don't know if it's going to be greater than or less than. And we can't peek ahead and look at our samples our sample proportion and decide the direction of the test at that point. All of this is based on the original hypothesis of not equal to. Now, we're not going to put 10% in both tails. We're going to divide in two for a two-tailed test. So you've got 0.05 here and 0.05 here, half of it. Those two together give us our alpha. This creates two reject regions. You would reject if you get a sample proportion that's extremely larger than 0.53, and you would reject if you get a sample proportion that is significantly less than 0.53. Two reject regions for a two-tailed test. In the middle is the do not reject region. And the only thing we can reject is the null hypothesis in a hypothesis test. The critical values, now there are two. Critical value, this is the lower one, and this is the upper one. Critical values, and these come from a normal distribution. And so you may recall that this z of alpha over 2 is equal to inverse norm, because now we're dealing with the normal distribution and not a t distribution. The left area is 0.05, and then we give the mean and standard deviation for the standard normal. And you might remember this number because you've calculated it a lot. Negative 1.645. And this one over here, also inverse norm. You probably already know what this number is. But if we do the left area here, we've got all of this 90 plus this 5% over there. So it's 0.95. And this is, in fact, just the opposite of the negative one. All right, now we're ready, except for the last step. Identify the sampling distribution. Okay, we did that by saying, hey, this graph is about the Z distribution. Sketch and shade alpha on the graph. Well, since it's a two-tailed test, we had to divide the alpha into two tails. Half of the alpha on the left and half of the alpha on the right. Identify the reject regions. Now there are two. And the do not reject region in the middle on the graph. Plot the critical values. Here they are. They correspond to the alpha. And the last thing is to shade the p-value with a different color shading. Okay, so the p-value is connected to the test statistic. So I'm going to go back up, find the test statistic. There it is, 1.657. Well, if this is 1.645, then so this is the test statistic, 1.657. It's just a little bit larger than 1.645. And you know, this is reflected in the fact that our p-value and our alpha are very close. Since our p-value and our alpha is very close, that means our critical value and our test statistic will be very close along the horizontal scale. So this is what we or this is what we call the Z test statistic. So these numbers, our critical values, are Z's, and the test statistic is also a Z. So you plot the Z values along here, two different kinds, and then the area, if you draw from your test statistic and something more extreme, then this is half of the p-value. And so you have to do a mirror image of this over here, and then this is half of the p-value. And you add those two together to get the p-value. So once again, you can see that when you add the two red regions together, the p-values, to get the p-value, that shaded region is less than the alpha region. So p is less than alpha, and that means we're going to reject the null hypothesis.